So today we were looking at internal erosion into a levee. There's a number of different failure modes that occur during internal erosion, and we chose to model internal erosion into a culvert. During that process, there is a culvert defect. Maybe it's a misaligned joint or a crushed section or some sort of erosion that occurred, and water is able to start seeping into that culvert during its normal seepage path. And when it does that, sometimes it takes some of the fine grains of the soil with it, and so the erosion channel eventually can propagate and create total failure of the levee. Understanding this process is kind of multifold. This particular project, we really wanted to know what kind of early warning signs might there be so that we can fix a problem before it gets too extreme. And two, we wanted to see, can instruments or monitoring help us identify odd changes or things that we wouldn't expect.
We had to make a false bottom for it to build the levee on top of so the water could come off the other end. We had to make a soil catch and a V-weir to measure outflow. We had inflow and outflow readings on it. We had PPT, pore pressure transducers. So we've had a bunch of different sensors on it. I think we finally got it down to an art now. So what started out as a 2-week deal for us to build a levee, we can do it in 2 days now.
We saw in test 2 that a little bit before it reached the surface, we could see a bit of a seepage path through the IR camera, but it still would have been a little too late in the real world. So I think it's a promising technique, but there's definitely more research that needs to be done before it can be used in the field. It's always a team effort. Our technicians are amazing at helping us figure out, okay, we have this grand idea, how do we make it a reality? And we'll work with our technicians of like, okay, we think we have these parts and this might work well. What do you guys think?
When you think about centrifuge modeling, you would never think, I want a carpenter or I want a mechanic, but essentially it's all of the things that you've learned go into centrifuge modeling.
On test day, you really want your test to be a success, but sometimes you just don't know if some of the things you put on the model are gonna work. Sometimes you don't know if a certain motor or a certain screw is gonna work at 20 G. You never really know what's gonna happen until you spin it up. It can definitely be a little tense, and usually it's because we all care so much and we're really excited to see what might happen, what can we learn from this, and what problems can we solve. On this project, we worked with Virginia Tech, so they are doing MPM modeling, which is the material point method, and they're able to model large deformations using numerical modeling. In numerical modeling, it's much easier to run different simulations, try different sizes, that sort of thing, but it's not always validated. So in the centrifuge, we can run a few tests and really help validate their model, and using the two of them together can really help tell a story and shape our understanding.